Okay, so welcome everyone. It is a pleasure to introduce Umang Mathur, who is faculty at NUS. Umang has done some amazing work on data race detection, and he's the recipient of the Google Research Award and a few Best Paper Awards. And Umang, you can take over, and we're looking forward to your talk.
Thank you, Akash, and thank you, IARCS, for the invitation. This work that I'm going to talk about today is primarily coming out of my PhD research. I only started my faculty career about a year ago, and so let me sort of before going into the crux of the talk, let me sort of start by stating some rather obvious background, which is on concurrency and why do we care? So most software applications today exploit concurrency in direct ways. So from web applications like web servers and browsers to operating systems, mobile applications, or data intensive applications are all designed to exploit concurrency in significant ways. Okay. In fact, it'll be fair to say that concurrency-centric advances in both hardware architectures and software frameworks have played a prominent role in today's AI revolution. At the same time, concurrent programs or concurrent software still remain challenging to develop and to sort of write correct, and they're also tricky to get right. And that's because these programs are non-deterministic because of thread scheduling, which does not have an explicit directive, and thus developers, when they write concurrent programs, even if they have to do very simple reasoning about their programs, they have to essentially reason about all possible interleavings, which is very challenging and error prone, and that is why bugs like data races or deadlocks regularly manifest in production level software. Data races, in fact, are known to be the worst enemies of programmers. They're hard to detect, debug, or even reproduce. So just to sort of set context, data race is something that occurs when the program accesses a common or a common memory location, which is sort of shared across all threads by two different threads at the same time or concurrently, and there is no explicit synchronization between these two accesses. So that's what a data race is. At this point, I'd like to sort of talk about one of the ways that we can sort of detect data races. It's called dynamic analysis, wherein you observe an execution of the program and then analyze the execution and figure out if that execution has a data race, and therefore whether the program has a data race. So this is sort of slightly different from something like static analysis, where you, instead of observing executions, you look at the source code and then analyze the source code to determine if there's a bug like data race. And it's important to state that when we want to sort of aim for finding bugs in industrial level software and not toy programs, it makes sense to focus on something that gives you sort of concrete witnesses of data race bugs. Static analysis, on the other hand, is not so much catered towards this property. Typically, static analysis are designed for sort of certifying that a program does not have any bug like a data race. But oftentimes, typically, your program will have many data races or bugs, and you will end up getting a lot of false alarms. So that's why dynamic analysis is the rather preferred way of detecting data races in the industry. In fact, the kind of techniques that I'm going to talk about in this talk go beyond just the simplest setting of detecting data races from executions. In fact, even things like fuzzing essentially use some sort of dynamic analysis as the crux to detect concurrency bugs. Or if you talk about model checking, that is essentially also the same as exploring many executions and then figuring out which of these executions lead to a bug. So the kind of techniques that I'm going to talk about here are sort of broadly applicable and not just limited to dynamic analysis as such. Anyway, this talk is sort of a little bit more algorithmic in nature. The kind of things that I'm going to talk about a little bit more on the algorithmic side instead of on the practical side. And when we're talking about algorithmic properties, it's important to emphasize that there are certain desirable properties of a dynamic analysis technique that we want. So the first property that I am looking at is soundness. Soundness meaning that the analysis that I want to design does not report false positives. The second property is that we want our analysis to be usable. And by that, I mean, it should scale to large traces coming from modern software applications, which typically have millions or even billions of events, even if I run it for, let's say, a few minutes. Finally, one more desirable property is high recall, or as I like to call, high prediction power, which means that the technique that you want to design does not miss many races. And so these properties are often conflicting, and for a large part of the history of race detection, getting a good balance has been really hard. And in this talk, I'm going to sort of talk about some recent advances that have achieved this balance. Okay, so with that, let's delve into some technical details. I'm going to consider concurrent programs with shared memory. And on the left, I have an example of such a program, which is sort of a Java-like program. So these programs have threads. Here, the main thread corresponds to one thread, and it creates two. So here there are two threads, T1 and T2. Now, threads can read or write to shared memory. Here, the static variables X and Y are basically the shared memory. And there are also, other constructs like locks, which enable things like mutual exclusion. And of course, this is an example of an execution. So an execution of such a program is basically a sequence of events. Every event tells you what is the thread that performs the event, and what is the operation that was performed in that event. So for example, if you look at the first event, that is performed by thread T1, and it is an acquire operation on the lock L. Similarly, if you look at the fourth event, that's a read event on the shared memory location X, and that's performed by thread T2. So these are the kind of operations that you can have in your executions, and that's the kind of setup that I'm going to look at. Okay, so now let's look at a little bit more fundamental definitions. So let's first define data races. Okay, so the way I want to define data races is as follows. So I'm going to look at executions, and I'm going to say that an execution has a data race. So remember, an execution is a sequence of events. So such an execution has a data race if there is a pair of conflicting events which are concurrent. So a conflicting pair of events is basically something that I've already told you. These are two events which are accessing the same memory location, and they are performed by two different threads, and at least one of them is a write. So both of them are not read events. And when I say concurrent, there are many different notions of what it means to be concurrent. For this talk, it makes sense to sort of look at the simplest notion called basically that the two events are essentially occurring next to each other in the execution. So that's the definition of a data race. And here is an example. So this is an execution of 4 events. And as you can see, the second and the third event are conflicting events, and they're consecutive. So this execution has a data race. And when an execution has a data race, we also say that the program that generated the execution also has a data race. So with this definition, detecting data races sort of admits a very simple algorithm, right? You execute the program, you observe the trace, and then if you check if the data race exists in the observed trace. Now, this sort of simplistic algorithm is not that great, in the sense that it is prone to missing data races. Okay? In particular, what might happen is that you might run your program once, maybe twice, maybe even 100 times, and you might get the same execution, which may not reveal the data race, even if there might really be a data race, possibly also easily detectable. And that's because, concurrent programs are sensitive to thread scheduling, and you may not get the interleaving or the execution that you're looking for. But not all hope is lost, because there are certain techniques that you can use to sort of increase the coverage of this simplistic algorithm. So let's look at some example. Maybe let's look at this execution on the bottom right. So as you can see, this is a very similar execution as the top left, as the top right. But this one, unfortunately, does not have the conflicting events next to each other. So if I go by the definition of data race, I would say that this is not a data race. So this algorithm will not work. But as you might have also already observed, if I try to reorder the fourth event, which is the read of X, up above so that it comes between the write X and the release of L in 31, that would give me the first execution. And that the first execution, as we've seen, has a data race. So in a sense, I can reorder executions to expose data races. And that's essentially this notion of this concept of data race prediction that I'm going to talk about in this talk in a little bit more detail. Okay, so since the audience is pretty small, I can afford to sort of pause and ask if you have any questions. If not, I'll sort of move forward.
Yeah, Umang,
so it's a little bit, can you please be a bit louder?
What do you mean by consecutive? Just if there is some other event between that is not related to X, does that still become non-consecutive?
So you're right. You can in general sort of enhance this definition of data race and say things like maybe it's okay for them to be not consecutive, but maybe there are certain events in the middle which are not related, or there's a more sophisticated definition that you can come up with, which says that there is a prefix in which both the two events in race are enabled. All these definitions are sort of similar to each other in a sort of precise sense. The technique, but even with that definition that you're talking about, I would still not be able to, effectively do data race detection. Does that, and data race predictions still sort of makes sense. This makes sense in that setting. So the example that I showed you, of course, is very simplistic and does not sort of bring out all the things that you're talking about. You're right. But it's not really different.
Okay, so what I thought was, should that consecutive be to the say memory location? And okay, so when you're saying consecutive, meaning acquire and release are not in between, right? In between those two.
By consecutive, I'm actually saying that they occur next to each other. There's no event in between.
Okay, but if it is let's say write X followed by a write Y followed by a read X, would that write of X and read of X they still be racy, right?
They're still racy, but by this definition, that's not a data race. But anyway, you're right that I could have come up with a better definition, which says something more complicated, like there is a part of the trace such that the two events are maybe not next to each other, but in between those two events, there's no pattern that gives you a communication between these two events.
Okay.
But it's not really different, is what I want to say. Okay, and maybe some of the later slides will sort of clarify why I'm saying that. Okay, any other question?
One question.
Yes.
Srivatsan here.
Hi, Shri.
So I missed why we can't do a static analysis to detect data races.
I'm looking at unbounded domain programs, and so I want to have a way to sort of definitely report true positives, not false positives. I mean, it's an undesirable in general.
No, sorry. So like I don't understand how the domain is playing a role here, because I mean, you want to see if there
So
are
there are
consecutive, yeah.
no, so this, yeah. So if your program has loops
Yeah.
and conditionals and stuff like that, an unbounded domain, then you cannot predict whether there is an execution which might give you this kind of a pattern.
Okay. I see. Okay.
Yeah.
Okay. Okay.
Yeah.
Thanks. Yeah.
Okay. Any other question?
So just a quick, maybe you'll probably be taking up this point subsequently, but so you mentioned about some reordering, right? I mean, that's what you're
Yeah.
going to do.
Yeah.
And I was just wondering whether, would this reordering take care of this, that it doesn't change the semantics of the program, or
It
would you?
will. It will. It absolutely will. Yes, that's one of the fundamental points about something that I'm going to talk about.
Okay, I'll wait. Thanks.
So, yeah. Okay. Okay, I think I should move on. So yeah, so as I said, I want to sort of do better than the naive algorithm of detecting these consecutive pairs of events. And the basic idea that I want to adhere to is this idea of reordering. And that's what I call prediction. But before we go on to sort of delve deeper into what is prediction, maybe let's ask even a more basic question, which is what are the kinds of reorderings that make sense? And let's look at some examples here. And that'll also answer one of the questions that was asked just a minute ago. So if I have an execution, so let's say I have this execution on the left, then let's say I want to sort of report a data race between the write y and the write y in thread T1 and T2, which is the third event and the last event. And right now they're not consecutive. So if I need to do some reordering, and the kind of reordering that I'm going to do is basically I'm going to move the read x and maybe also the write y, subsequent write y, up above the write y in T1. So I want to sort of place the read of x in between the write of x and the write of y. And this reordering in some precise sense makes sense. Okay, intuitively also it sort of gives you this reordering. This reordering is okay. This is an execution that I think makes sense. And all of the audiences will not mind that this is an okay reordering, I think. But let's look at the same execution here and let's try to sort of do this kind of reordering, wherein I want to place this write of x up above the right. I want to place this read of x in T2 up above the write of x in T1. And at this point, I want to argue that this may not be, the best way to do reorderings. So for that, let's look at this intermediate, this program in the middle. And as you can see, this is one possible program that might have given rise to this execution. So let's look at this in a little bit more detail. So let's say initially both x and y are assigned to 0, and then have two threads T1 and T2. In the first thread, inside the critical section of locl, I do x is assigned 42, and then I assign 1 to y. And then in the other thread, I read the value of x, I check whether it is 42, and only then I do a write of y. Okay, so if my goal was to detect a data race on write of y, if I do this reordering, basically it would mean that I read the value of x before it was assigned to 42, which means I would be reading the value 0. And if that's the case, I would not even go into the conditional in thread T2. So in that sense, this is not a reordering that I want to look at. So bottom line is that I want to do some source agnostic analysis in the sense that I want to be sort of conservative, and I don't want to think about the possible program that the execution might have come from. Maybe if I had access to the program and if I wanted to do some analysis, I could have incorporated it. But for now, I think I want to only look at the execution without any understanding of the programs, because I would again go into this sort of whole class of static analysis, which are expensive, yada, yada, yada. So I want to focus on source agnostic analysis. And in that setting, basically some reorderings may not be allowed. Okay, because there might be some programs that might disallow these reorderings. But nevertheless, some reorderings are always allowed, independent of the source program. So let's sort of formalize what I really mean by this, and let's come up with a definition of what is the class of reorderings that are allowed. So again, I'm going to stick to this principle that I showed on the last slide, which is a reordering is allowed if any program that gave rise to that sort of gave you the first execution to begin with, the observed execution, any such program will also be able to generate this reordering. So that's when a reordering is allowed. So how do I sort of come up with a definition that satisfies this property? Well, here is the definition. So a reordering must satisfy these properties. The first property is that by reordering, I should not come up with something that doesn't even make sense. So it should be a well-formed trace. It should preserve log semantics. So by that, I mean that critical sections on the same log don't overlap. So for example, if I look at this execution, I cannot reorder it like this. I cannot sort of place the acquire L alone in between the write X and the release L in T1, because that would violate log semantics. But I can place this entire critical section up above the first critical section in T1, because then critical sections are not overlapping, and that's an okay reordering. Similarly, I want to sort of say that because I don't have access to the program, I want to preserve the intra-thread ordering. In that sense, I cannot reorder so that the write X comes out of the critical section in T1. Finally, I also want to make sure, again, because I don't have access to the source code, I want to ensure that whatever reordering I do also preserves the control flow, which means that I want to ensure that every read event in the reordering also observes the same write as in the original execution. So for example, here I cannot do this. I cannot reorder read of X in T2 before the write of X in T1, because then it would see a different value. It might see a different value. Although, if I were to place this read of X between the write of X and release of L, that would be okay. So this is what we call, what people have called a correct reordering or a feasible reordering. And that's sort of a fairly established definition at this point. So I'm going to pause for maybe 30 seconds more just to see if there are more questions.
Yeah. Hi, Umang. This is Abhishek. So I have a question on the third point where you say preserve control flow. How do you know that? I mean, since you don't have access to program, how do you know that you are not reordering with respect to write? I mean, original write. What do you? So every read sees its original write, right? So
and that is enough to ensure that control flow is preserved.
Yeah. So how do you ensure that original write has not been? I mean, how do you even know that which is the original write for a read?
So this is the definition, right? So I'm given an execution in the beginning, and the question I'm asking is, what are the kind of permutations that are allowed? So a permutation or a reordering is allowed if, okay, so I'm considering this very sort of basic, what is called consistency model called sequential consistency. And under this consistency model, I can assume that every read observes the write that was just before it.
Okay, I see. I got it. Yeah.
And just another related question. So is there a sort of memory location of interest in this case, for example, X? But if, like the example which you showed, if this read of X in T2 also has a write of Y under if condition, and that would change the semantics of Y, but you don't bother about that, right? I mean, that doesn't affect your analysis.
Sorry, what are you saying?
So I'm saying that if read of X moves over here, it moves above. So write of Y will also move because the whole block has to move.
Okay. I mean, not necessarily, but sure. Okay. Let's say, yeah.
Because, okay. So you're saying that even the structure of the code could be changed. The read of X you could retain over there, but you would introduce a new read of X immediately after the write of X in T1. Is that what you'll do?
Yeah.
Okay, got it. Thanks.
Any other questions?
No, sorry. I think you can't introduce a new read, right, Umang? You can only move that.
Yeah,
read.
so by introducing, I mean, instead of performing the read after the release of L in T1, I perform the read before, let's say, the write of I in T1. So I'm only coming up with permutations. I mean, it's more like subsets of permutations, subsequences of permutations at this point.
So can you view this execution as a partial order in which you have, I mean, one is the acquires happen after the releases. I mean, you know, there's a
Yeah, so I'm going to talk about that partial order also.
Okay,
and
okay.
I'm going to talk about how that's not a, you know, not the best way to think about executions.
No, I mean the way or reordering you're describing, I'm asking, can you view that as a linearization of this partial order, where I mean you have release to acquires and you also have the write scene edges.
Maybe a simpler partial order to think about is that you just have program order and you have these reads from edges and no acquire release edges.
Okay.
And of course, not all linearizations are going to be sort of valid executions.
Right.
Yeah. So valid executions are those linearizations in which critical sections don't overlap.
Mm-hmm.
And also a later write does not come in between a read and its writer.
Right. And that's preserving the last scene.
That's
right?
exactly, yeah.
Mm-hmm.
And that's this condition. So all the things that I said right now are exactly the three conditions that are here.
Mm-hmm.
So you don't change the thread order, so you preserve the program, the thread order. You also preserve the log semantics, so you don't overlap critical sections. And you make sure that no other write comes in between a read and its writer.
Okay, so moving, you're allowed to move critical sections, and that's not allowed in the partial order that I said, right?
Yes.
Okay.
So the first example in this slide, in the top one, I am allowed to move the critical section.
Right.
But if I place an edge from release to acquire, then I'm forced to not reorder.
Okay.
Okay, let's move on. So it's a good time to recap this picture again. I told you that an ideal race detector must offer a good balance of these three properties: soundness, scalability, and high recall. And data race prediction is a key idea behind how to enhance the predictive power while ensuring soundness and also at some time scalability. Okay, so let's sort of revisit data race prediction. So the problem at hand is you have an execution sigma and you want to check if there is a correct reordering. The correct reordering definition is something that I talked about in the last slide, in the last slide maybe, with the data race. So basically the picture looks like this. You have an execution which you observed, and there is a space of correct reorderings, which are essentially all the possible reorderings that you want to reason about. And maybe in one of them, there is a data race, since that's what you want to detect. And basically the definition of correct reordering also ensures that if you do find this kind of a this new correct reordering with the data race, it also means that the program is guaranteed to have a data race, because correct reorderings were such that any program that would have generated the observed execution would also generate this correct reordering. Okay, so let's look at existing techniques. By existing techniques, I really want to say that techniques prior to the kind of things that I'm going to talk about in this talk. Yeah, so the best way to visualize this sort of the space of existing techniques is using this 2D plot. On the x-axis, I have scalability, which basically measures if the techniques are able to handle large executions. And on the y-axis, I have predictive power, which is a measure of how often I'm able to report a race in some correct reordering. Okay, so on one hand of the spectrum, there are techniques that resort to basically enumeration. If you have a trace with n events on k threads, the number of possible reorderings is of the order of k to the n. And these techniques essentially enumerate all such reorderings and check whether any such reordering has a data arrays. But as you can imagine, scalability is really a bottleneck in these kind of techniques, even if you resort to some kind of a constraint solving based symbolic search. On the other hand, we have on the other spectrum, we have this most widely adopted data race detection techniques, which is based on this classic happens before partial order. So here, instead of looking at all possible correct reorderings, one restricts themselves to a small number of reorderings and data races that can be found within those reorderings. So the first kind of techniques do all possible reorderings, and they resort to exponential search. And this happens before kind of techniques resort to a small space of reorderings. But the advantage is that there are algorithms that run in linear time and detect races in these reorderings. And so let's actually look at happens before. This is something that Deepak has also already mentioned, but I want to look at it in a little bit more detail because my work, and in fact, a lot of other works have been inspired by happens before style reasoning. At the crux of it, happens before is a partial order. So if you have an execution sigma, it's a partial order on the set of events of that execution. So what are the kind of orderings that you place? The first kind of orderings that you place are these intra-thread orderings. So, between any two events of this of a thread, you place an ordering from an earlier event to a later event. And the other kind of edges are these release to acquire edges. So if you have two critical sections on the same log, you place an edge from the release of L of the early critical section to the acquire L in the later critical section. And of course, it's a partial order, so you have transitive closure also. And now, if you want to detect a race, you say that there is a race if there are conflicting events which are not ordered by this partial order. Okay, so that's the criterion for detecting a data race using this partial order. And it turns out that this criterion is sound in the sense that there are no false alarms if you use this criterion. By false alarm, I mean by sound, I mean if you say a race according to this criterion, then there will be a correct reordering in which two events which are conflicting are next to each other. Okay, so that's the guarantee. So that's the soundness guarantee. And now this very simplistic partial order also admits a very nice algorithm which runs in linear time. It sort of processes events one by one, and then as soon as it detects a race, it reports it. It's a very nice sort of scalable kind of an algorithm. It's a monitoring algorithm. So here, if you look at this example on the right, all the events are actually ordered because it's a partial order, so it's transitive. And so HB will say there's no race, but as you might have probably guessed, that there is a race that I can actually expose by reordering. I can reorder the right so that the right of X actually comes, after the right of X in T1. So this kind of reordering, and as you can see, this reordering gives you a data race, and this is a correct reordering because it doesn't violate any of those things. There are no reads, so of course no control flow is violated, no critical sections are being overlapped, and also thread-wise, I'm not changing order of events. So basically, the bottom line is that HV is too conservative, and it misses simple data traces, even though there are many good things about HV, especially its soundness and its efficient algorithm, and that's what we want to sort of tackle. And I'm going to talk about it in a little while after a 30-second pause, maybe. Are there any questions?
Yes, thanks for making these pauses. So is it something which is specific to this locks? So if you consider something without locks, does HB detect all data races?
Yeah.
Okay. Thanks.
I mean, so you have to be a little bit careful. So the soundness guarantee that I say is basically that if you're given an execution and if you use this criterion, And if you do find one such pair, then the guarantee is that there will be a data race. It's not like I will be able to, it's not like all pairs of data races are going to be unordered. Rather, there'll be some pairs which are unordered, but they should not be called data races. But if you're just looking for the existence of a data race, that's a sound and complete algorithm in the absence of logs.
Nice. Thanks.
Any other question? Okay, if not, let's move on and try to make happens before better again. So the first technique that I'm going to talk about is this something that we did. Now it's a 5-year-old thing.
So Umang, sorry, in the last slide, so you could say that even your technique also misses some races, right?
Yes.
So I mean, it's just a question of where you draw the line, and I guess as a trade-off, how efficient you are. And
that's right. Yeah. So generally, my efficiency metric is that let's focus on linear time algorithms. If you can in linear time detect more races than happens before, probably better.
Right. Okay. Makes sense.
Okay. Any more questions? If not, let's move on to the first class of techniques that I'm going to talk about. And before I get into the details, let's understand the most obvious questions, which is if I want to tackle the conservativeness of happens before that I pointed out in the last slide, I need to understand the kind of reorderings that happens before reasons about, which is essentially the space of linearizations of that partial order. And the point is that the partial order is too conservative. It orders too many events, and therefore it misses some reorderings which are not linearizations of this partial order. Now the question is, can we relax some of these reorderings? If you naively relax these reorderings, you might end up in linearizations that are not even correct reorderings because you might overlap critical sections, for example. And therefore, in fact, on the other hand, if you try to do a very careful analysis on and figure out which are the reorderings that you want to relax, that's again, you're going to go back to the same problem because then you'll be doing some expensive analysis, etc. So you don't want to do that either. And so the question that I want to answer here is, can I balance both soundness and scalability and still get better prediction power than happens before? And WCP is the answer to this question. So what is WCP? WCP, or weak causal precedence, is again a partial order. And it's a systematic way to essentially identify when to order critical sections on the same log and when to not. So WCP, like happens before, is again given in this rule-based style. So it's again a partial order on the set of events of this execution. The first rule says that if you have two critical sections that contain conflicting events, then you should not reorder these critical sections, which means I should place an edge between the two critical sections. So the precise rule is a little bit more contrived. It says that if you have two critical sections on the same log and they have conflicting events, then you should place an edge from the release of the first critical section to the read of X in the second critical section. Okay, instead of like HB placing release to acquire edge. So let me tell you why that's the case, why it's a little bit more contrived. The first reason is that it's a little bit more relaxed than what you would get by release to acquire. Okay, so it's in that sense better. And in fact, the reason why we chose to come up with this rule was because, if you did release to acquire, it turns out that you could not detect this partial or construct this partial order in linear time. So that's another reason why we chose this kind of setting. And finally, all of these decisions have to be backed up by some sort of soundness guarantee. So it turns out that soundness works out well. Anyway, moving on, the next rule is that basically if you have two critical sections that are inductively ordered, that contain events that are inductively ordered by WCP, then again you should not reorder these two critical sections. So in that sense, WCP is a recursively stated partial order. So here is the precise rule. So it says that, let's say if you have two critical sections C1 and C2, which contain some two events, E1 and E2, which so far have been ordered by WCP, then you order the release to the release instead of release to acquire. Again, the same reason for why this sort of a little bit more involved, a little bit more relaxed partial order. And finally, yeah.
I have a question. So you said ordering from the release in the first thread to the acquire in the second thread would make the analysis expensive. How does that change if I order the release of L to the read of X in the second thread?
So you're talking about the first rule?
Yes.
So you're saying instead of release to...
If I understood correctly, one of the reasons why you clean the edge from the release of L to the read of X in the second thread, one of the reasons is, if I understood correctly, was that you said, this is cheaper to compute, to track. So why would that be compared to if I had actually drawn it from release of L to acquire of L like L?
Yeah, so if you look at these two rules together, you can see that there is some sort of induction going on. So what might happen is, so actually the first rule is sort of easy to explain in that sense. So you're saying instead of placing release to read of X, you want to place write X to read of X? No.
No, I'm just saying that, how would the analysis become more expensive?
Okay, yeah. So if instead I were to place... Yes, so if I were to place release to acquire, basically what I need to do then is that I need to sort of have some information of the earlier critical section when I'm reading in the later critical section. And when I see an acquire L, I don't know the future events. I don't know whether a read X is going to come in the future. So I need to also sort of store the acquire L until the point I see the read of X. And then when I see the read of X, I have to go back and then say, oh, you know what, that acquire L must be ordered after the earlier release of L. So there is some sort of a back and forth that has to go on if I have to sort of go this. But instead of that, this rule basically says that you don't need to remember acquire of L because I'm not really ordering.
So at the read of X, you don't need to maintain the history of the thread tools or whatever critical section you were. It could be a large unbounded critical section. Okay, thanks.
Yeah. Okay. Yeah. There's another question. Okay. So I'm not able to hear if there's a question.
Can you hear me?
Yeah.
So since we have placed the release before read and not before the acquire, doesn't that allow that the acquire will be within the critical section?
Yeah, so there will be linearizations which are not going to be well formed, but the soundness guarantee doesn't explicitly talk about linearizations. So you're right that if you really look at linearizations, some linearizations will not make sense. But the soundness guarantee does not even talk about that. It says if there are two events which are unordered by this partial order, then there will be a correct reordering. Of course, coming up with that reordering is a little bit more involved, but nevertheless it works out. So you're right. There will be some linearizations which are not correct, which are not even executions to begin with. But it doesn't matter. Yeah.
So if there are two conflicting events which are unordered, then there will be a reordering which will have a data race. So will these two events be the racy events? Like, is that guaranteed, or are you only guaranteeing that there will exist some pair?
If yes, so there will be some pair. They need not even
from the one that we found unordered.
Yeah. In fact, the soundness guarantee is actually even more involved. It says that sometimes there may not be a data race, but then if that's the case, then there'll be a deadlock.
Okay.
Yeah. Okay. The final rule is sort of essentially there to ensure soundness, because these two rules by themselves are not enough to ensure soundness. It says that this partial order is also it's closed under composition with happens before. So happens before is that earlier partial order. So this rule says that if you have two events, E1, E2, which are ordered by WCP, and then E2, E3 are ordered by happens before, then you should place an edge from E1 to E3. Likewise, if E1, E2 were HB ordered and E2, E3 were WCP ordered, then again you would place an edge from E1 to E3. So this rule is basically, it's hard to give an intuition for why we have this. It's basically there to ensure some soundness. So let's talk about soundness now that we are already there. So this is the guarantee. The guarantee is that if you have an execution sigma, and if you have two events, which are a pair of conflicting events, and these two events are also unordered by this partial order, then there is a correct reordering of this execution, which exhibits either a data race or a deadlock. Okay. If there are questions, please interrupt. Otherwise, I'll just move on. So just to sort of give you the broad overview again, how does WCP compare with HB? The first point that I want to make is that the HB is a stronger partial order than WCP, and that means that every race that HB reports is also going to be reported by WCP. It orders WCP orders fewer events. Not just that, there are examples where WCP does in fact detect more races than happens before. And the intuitive difference between HB and WCP is that HB naively orders all critical sections on the same log, whereas WCP selectively orders them. Now, the silver lining is that WCP admits a linear time algorithm for race detection. In some sense, it's a very similar algorithm to happens before. You do need some extra bookkeeping, but at the end, it's a linear time algorithm. And therefore, if I go back to the same picture that I've been talking about for a while, WCP would sort of lie somewhere here. In fact, we did some experiments on some benchmarks, and we figured out that it in fact does better than even the symbolic search kind of techniques, because they in practice have to limit their search space. WCP can do better than what they limit. And in terms of scalability, is as scalable as happens before. Okay, so in the interest of time, I think I should maybe only sort of give you a very brief overview of what this other work is. So this work is a little bit more recent, and it's again an attempt to design another algorithm for detecting data, for predicting data races. The kind of data races that it predicts falls into this class, or is exactly the class of races called synchronization preserving races. And let me sort of tell you that the principle behind this kind of these kind of races is that we want to go back and sort of rethink why we did not like happens before. Instead, we want to actually go back and rethink why we liked happens before. The reason we liked happens before was because it was scalable. And the core principle that gave you scalability was that all critical sections of the same log were ordered. So if you are at a critical section, you're going to sort of order all the previous critical sections before it. And so the question that we ask here is, can you maybe use the same principle, but slightly differently, and still get better prediction power than happens before? And the answer is yes. So I'm going to define what these races are. And instead of sort of looking at the algorithm, et cetera, we're just going to move on to the next segment of the talk. So here is an example. Here, let's look at let's look at this execution. Observe that I can actually reorder this execution in this manner. So this is a very special kind of reordering. I am actually dropping events. I'm forgetting some events, but it is nevertheless a correct reordering because, again, whatever events you have, thread ordering is preserved. Also, critical sections do not overlap. And if you look at, so here the read of X and the write, the read of X observes is also observing the same write. So in that sense, it's a correct reordering. But it might sort of defy your intuition in the sense of, can you even drop events? But you can. So this kind of a reordering is actually a synchronization preserving reordering. And such a reordering is a reordering wherein whatever critical sections you have remaining, their order remains the same. Okay, so in general, correct reorderings allow you to also reorder critical sections. But here I'm saying, just like it happens before, you sort of maintain the order and critical sections of the same log. You are allowed to drop critical sections, but whatever critical sections remain, you have to sort of keep the same order of them. So that's what a synchronization preserving correct reordering is. And so now you can define what is a synchronization preserving race. Basically, if a race can be discovered using a synchronization preserving correct reordering, then that's a synchronization preserving race. So here, if you look at this example, WCP, the partial order that I talked about in the previous slide, in the previous segment, would actually order these two write Y events. Because if you look at these two critical sections on lock L and T1, T2, they contain conflicting events, which means they will be edged from release of L and T1 to the write of X and T2. And because it's a partial order, you will also get an ordering from write of Y to write of Y, because you will also add thread ordering constraints. So WCP will also not be able to detect this data race. But if you sort of take this alternative view of, that you're allowed to drop critical sections, you would be able to discover this critical section, this race. And of course, I'm presenting it in some well manufactured way, but the basic reason is that we had an understanding that if you allow yourself this flexibility, then you can come up with an efficient algorithm. And that's the point. The point is that there is a linear time algorithm for detecting these kind of data races. I think I'm not going to go into any more details, but the point is that these three things that we've talked about so far happens before WCP synchronization preserving races are sort of, this is how you should think about them. Happens before, orders all critical sections in the same lock. WCP identifies when to order critical sections. This third notion that I just introduced essentially identifies when to drop critical sections. So if I want to sort of look at a Venn diagram, this is how the Venn diagram would look like. The yellow rectangle is essentially the set of all predictable data races. The pink, the red or the pink oval is the set of synchronization preserving races. The green one is the WCP races. So, they only have a common intersection. It's not as if one is a subset of the other. But anyway, the common intersection strictly happens before HB races. Okay, so this is how,
Sorry, Umang, could you please re-explain the benefit that I get from sync preserving races compared to WCP, assuming that, given that sync preserving is not a superset? So
benefit in the sense of,
I understand that, in the sense of data race coverage, I understand that this was an example where sync preserving could expose the race where, WCP was ordering it. So basically, there are few examples where sync preserving wins, right? But the set is disjoint as you were trying to show us. So then, from a practical point of view, how would I utilize these two ideas? Am I supposed to run two algorithms or two approaches on real world applications? So like, how is there a heuristic that I can use to choose whether to prefer to use WCP or sync preserving?
So of course, both are linear. So as you already sort of pointed out that you can run them in parallel because both are linear time algorithms. In fact, they both work in a manner that they process events one by one, and they're also both online. So you can run them in parallel. Having said that, in our experiments, we observed that most of the times sync preserving in practice detects all the races that WCP can detect. And it's also sound in a more stronger sense, in the sense that you can actually report multiple races using using sync preserving, and all of them will be guaranteed to be sound. To get similar guarantee from WCP, you have to add more edges if you want to go beyond the first race.
Okay.
So in that sense, in practice, sync preserving was observed to be better.
Okay. Thanks.
Yeah.
Umang, one follow-up question. So, does that mean WCP detection is a subset, can detect a subset? It's only a subset of the sync preserving races, or
theoretically it doesn't mean that. So there is no guarantee that sync preserving races. I mean, there's no guarantee that you will detect all the races that WCP will detect using sync preserving notion. But what I just talked about, what I told Swanendu a little while back, was that perhaps in practice, or whatever experiments we did, it turned out that we could detect all such races using sync preserving.
okay. So like maybe have you come up with like a artificial example at least, like which can be detected by
WCP, but I can talk about it towards the end, maybe.
Okay.
But yeah, even our paper has it. I think I have something in the talk, in later parts of the talk as well. I might not be able to go through them, but we can talk about it little later after the talk ends.
One question on the false positive. So sync preserving is deleting critical sections, right?
Yeah.
So does that increase false positive rate?
All the things that I've talked about do not report any false positives. So everything is sound in that sense.
That is surprising, because when you delete the critical sections, you are essentially admitting more spurious traces, right?
No, I'm not. That's the point. I am still ensuring that whatever reordering I'm reasoning about, again, whatever correct reordering I'm reasoning about, is essentially a valid reordering of the same program. Look at this reordering on this slide, right? The same program would have generated this reordering also, right? It's basically, I did some reordering and then I'm sort of stopping the program at some point.
Yeah, I guess delete is possibly a bit confusing here. Delete, basically, the critical section on the left hand side is just kind of getting delayed.
Yeah, I'm not. Yeah. So Swanendu's right. Delete might be confusing. I'm not deleting in the sense of deleting arbitrary things. I am cutting off suffixes of threads while ensuring sort of all those good things like control flow and no critical sections overlapping. Does that make sense?
So in a way, this critical section is getting reordered with respect to the right. Why is it?
The critical section is being reordered. Yes, that is allowed
within the same thread. So
in the sense, yeah, in the sense that yes, now earlier you were performing the critical section in T1 before you were performing write Y. Here I did not allow that. I did the write Y, and then I said, okay, now you don't care about the later events. I've already found a race.
Oh, yeah, okay. So in that case, so now we are admitting reordering within a thread.
No, I'm not. It's not a reordering, right? It's just like, so if you let the program run in thread, if you let the scheduler run and ask it to schedule T1, it would still schedule acquire of L. It might actually also schedule read of X. But this time the read of X will see a different value, so I cannot guarantee the later events. But the point is, I really don't care about those later things. The whole point was to only detect a race on write of I, and I could detect it independent of the later events. So the way I've defined correct reordering, it allows you to do some it's okay to sort of stop threads at some prefixes.
Okay, but it is in a way equivalent to allowing reorderings within a thread and stopping it after.
It's not, right? I mean, so yeah, it is not reorderings within a thread. It's how is it reordering? It's really,
So
I'm not changing the order of any.
So if that critical section occurred before the right while, or if you are
Across
moving the right
threads.
while to below the critical section, it would somewhat be similar to this ordering that we get on the right side.
So I think let's get back to it after the talk.
Okay.
Yeah. Okay. So, but anyway, so if there are student audiences here, I think it makes sense to also sort of talk about the kind of work that verification or programming languages people do, and it ranges from very practical work to even a little bit even more theoretical work as well. And so that's what I want to talk about here, and I want to sort of motivate that whatever inclination you have, this verification is a good avenue for your work. You can ask all sorts of questions, and that's what we did in this paper. We took a very practical problem and we asked very theoretical questions about it. In particular, we asked, how hard is this problem, right? We could of course come up with better and better algorithms, but is there like a limit to what is the best algorithm, or are there fundamental notions of hardness? It turns out that this is a NP-hard problem, and surprisingly, it wasn't sort of known precisely well. But nevertheless, there is a algorithm that runs in time n to the order t. So t is the number of threads and n is the number of events. And observe that this is a better algorithm than looking at all permutations, which would probably run in time k to the n, or even n factorial, right? So because typically the number of threads is smaller. But then it turns out that you cannot probably do better than this kind of an algorithm. In the sense, you cannot come up with an algorithm which runs in time strict polynomial in n, maybe multiplied by some function of threads, because we could show that there is a sort of some sort of hardness called W1 hardness, which disallows some such fixed parameter tractable algorithms. And of course, when we were looking at these kind of questions, we also tried to sort of come up with special cases where this problem becomes easier, quadratic time or sometimes linear time. And then we sort of continued this line of exploration, and we sort of asked even a more fine-grained question, which is basically, whatever techniques we've seen so far work in practice sort of are almost all linear time. But they're only linear time when you consider some of these parameters as constant, like number of threads or number of locks. And so the question that we wanted to ask was, again, can you actually come up with a purely linear time algorithm or not? And so here we sort of wanted to look at what is called as a fine-grained complexity of these notions. And this is a very, it's still under development kind of an area, even in complexity theory. It's called fine-grained complexity. And using some of these popular complexity theoretic conjectures like exponential time hypothesis, we could establish that most of these notions are actually not linear time if you consider these parameters as not constant. So you can establish quadratic time lower bounds in a lot of these cases. So I think with that, I'd like to conclude the talk by basically talking about some maybe practical avenues or even a little bit more theoretical questions. One of the theoretical questions that sort of is very close to my heart is that, can I come up with the best linear time algorithm, in the sense that I can come up with a linear time algorithm that will detect all races that any linear time algorithm can detect. And of course, on the practical side, the questions that make sense are, can I use these techniques to also find bugs which are different from data races, like deadlocks or atomicity violations? Finally, it's important to observe that the point that I stated in the beginning, which is that dynamic analysis by itself is, of course, one thing, but it also finds applications in other domains like model checking. And very recently fuzzing or even control concurrency testing. We have an expert here, Akash, who's doing a lot of work in control concurrency testing. And so the question that I want to ask generally is, do some of these techniques also improve these other techniques? And of course, you also want to ask similar questions in a slightly different paradigm, like message passing concurrency, distributed systems, or even weak consistency models. So with that, I'd like to thank you all for being a wonderful audience and also very engaging audience. And I also want to mention that if you're looking for positions or collaborations, I'll be very happy to talk. So please shoot me an email and we can talk more. Thank you.
Thanks, Umang. Any final questions?
Yeah, can I ask a question?
Yes.
Thank you very much for the very nice talk, Umang. So probably there's something which is you have mentioned in your future work. I was just wondering if you take your technique and can you make it into a complete algorithm?
Meaning?
In the sense, so you take one, you're taking one execution and then you're reordering, which is like saying you're finding another execution of the program since you have a sound guarantee.
Yes.
Right. So, and then, so can you extend this to say that, okay, now I've executed some bunch of traces and I've executed some bunch of reordering. This exhausts all the possible, executions of the program. I'm trying to get into a partial order reduction style algorithm.
So you're still working with one execution?
Yeah. No. So you start with one execution, you do all the reordering. So so something which is very simple is you start with one execution, then you look for another execution, then you look for another. This is the usual enumerated thing. For instance, then you take one execution, do all your reordering, then take another execution which was not dealt with before. Take
That's
all
what
the reordering.
This DPOR style model checking would be.
Correct. Yes.
Yeah.
Propelled by your technique, like.
Exactly. Right. Yeah. So yes, in principle, that's the idea. But yes, and it might seem simple, but when you actually go and do this kind of model checking, you have to also take care of the fact that you want the memory overhead, for example, to be fairly low, and you want optimality, for example, at some level, right? So it's not clear whether how far you can go with these kind of ideas.
Okay.
In a sense, it's really up to exploration.
Okay. So if I may ask one more quick question, so in the usual DPOR, there are also these bounded contexts which give some gain. Like you assume that your bug can be detected within a few context switches. So does that help anyway if you kind of make an assumption that data races can be detected within few context switches?
So we do okay. So in one of the papers, we did study some similar notion. Maybe I have mentioned this here, or maybe not. But basically, yes, there was some notion of bounding some parameter like that. Whatever result we came up with, it was again an exponential algorithm in terms of in the sense that the bound was appearing in the exponent.
I see. Okay.
Yeah, but you're right. That's also one way to.
Okay, that's okay.
Sort of explore. Yeah.
Okay, thanks a lot.
Yeah. Any other question?
Sorry, I was muted. I was just thanking you, Umang. Thanks for the talk.
Sure. Yeah, I really had a good time.
All right. Thank you. Bye, everyone.
Thanks, Umang.
Yeah, thank you.
Bye, Akash.